the path connected and connectedness. So just a minute. Yeah, path connectedness and connectedness. So that will be better. Okay, let's start assignment 4 problem. But before that, I'll just stop the presentation for a 1 minute, one more minute, please. Yes, we take 2 minutes. Okay, okay, sorry. I think I'll try to. Sorry. Okay, so this is the question, first questions. I'll try to copy here, but okay, that is not happening. Yeah, this is the first question. So what first question says that let x be okay. Now I am audible and my screen and all things are visible, right?
Yes, sir, everything is fine.
Ah, thanks. Yeah, just make sure that. Yeah, this is the first question. What says is that let x be a set with topologies tau 1 and tau 2 such that tau 1 is subset of tau 2. And let A is subset of x be given subspace topology and given subspace topology. If A is connected with respect to tau 1, then A is connected with respect to tau 2 or not. This is the question. Okay, so basically here one thing just I want to make sure, that what means that let X be a topological space. Let X be a topological space, and tau 1 and tau 2 are two. Let X be a set, and tau 1 tau 2, this is the two topology. X be a set, be a set, X be a set, and tau 1 tau 2 are two topologies, and let tau 1 and tau 2 are two topology on X. Okay, tau 1 subset of tau 2, that means every open set in X tau 1 is contained in the open set in X tau 2. Topology is nothing but the collection of sets, and those are called open sets. So when tau 1 subset of tau 2, that means the collection of subsets of X that is in tau 1, that is contained in the collection of subsets of X that is in tau 2. Okay, so now, so first what I will prove, that whether A is true or not, if A is connected with respect to tau 1, and let A is connected with respect to, and then A is connected with respect to tau 2 or not. Okay, so the counter example it is, let X is equals to A B 2 set, and consider tau 1 is equals to empty set and the full set X, that is the trivial topology, and tau 2 which is equals to, I am taking empty set, full set X, and the singleton set A and the singleton set B. This is the discrete topology. Okay, discrete topology. Okay, discrete topology on tau. Okay, discrete topology on X. Okay, now now let A is a subset which is connected, now A is equals to X, I am taking A is equals to X, then question whether A is connected or not. Clearly A is connected in tau 1. Clearly A is connected in X tau 1, because when A will not be connected, connected definition is giving via the disconnectivity. When a set is said to be disconnected, if there exists two open set A and B such that, or U and V such that non-empty disjoint open set A is said to be disconnected if A is equals to non-empty, there to exist two non-empty open subset U and V such that U intersection V and U intersection V should be non-empty. Okay, sorry, U intersection V should be disjoint. Sorry, U intersection V should be empty. That means U and V are disjoint. So there should exist two non-empty disjoint subset. Their union is actually A. Then we will call A is disconnected. But here A is connected because in this topology we can't write A as a union of two non-empty disjoint open set, because here is two open set. One is empty set. One is full X. So I can't write there, I mean, I can't get even two non-empty open set. Okay, so how can I write that is disconnected or disconnected? So this is connected. But note that here, note that tau 1 is subset of tau 2. So A is connected, but A is can be written A union of these two set B. Here, these two set are open in X with the tau 2 product topology, tau 2, sorry, discrete topology. That means A is disconnected. So if tau 1 is subset of tau 2 and A is connected in tau 1, that does not imply that A is connected in tau 2. So A is not true. Okay, first thing. Second, if B is connected with respect to, second is that if B is connected with respect to tau 2, then A is connected with respect to tau 1. That is the question. Okay, if B is connected, A is connected with respect to the topology tau 2, then A is okay. Now let A is connected. This is for B. Let A is connected in X tau 2. If A is not connected in X tau 1, so there should exist, so there should exist two non-empty disjoint open set U and V such that A is equals to U. Disjoint union is in general written by this way, but I can write direct union because they are disjoint and non-empty. You can write A equals to U union V. This is nothing but union. Okay, this sign is nothing but union, but that is in general written for disjoint union. Okay, so we can write, but as U and V are in tau 1, that implies U and V in tau 2 as tau 1 subset of tau 2. That means A can be written U disjoint union of V for two non-empty open disjoint subset. Non-empty open disjoint subsets or element U V coming from tau 2. That contradicts to the assumption that A is connected in tau 2. That A is connected in tau 2 or x tau 2. So x should be A should be, so A is connected in x tau 1. What we have proved that, suppose we have assumed that A is connected in x tau 2. Okay, if A is not connected in x tau 1, then we can write it as a disjoint union of two non-empty open set. Okay, so two non-empty disjoint open set, but they are non-empty open set in tau 1. That implies that they are non-empty open set in tau 2. That means I can write A as the union of two non-empty disjoint open set U and V coming from the topology tau 2. That will imply that A is disconnected in tau 2 topology, but that is a contradiction because we assume that A is connected in tau 2. So our assumption that A is connected in x tau 1, that is false. So that means A is connected in tau 1. So B is true. B is correct. Okay. So what we have said, A is false, B is true. Now connectedness of A does not depend on the chosen topology. That we have seen that connectedness depends on the chosen topology and automatically D is false. Is it clear?
Yes, sir. Clear, clear.
Okay. Okay. I think is this the second? Yeah.
Sir, second one is the direct result of the theorem, sir, proved in the lecture.
Right. Just that will be like connected if and only. I don't
Only if they are disjoint.
Yeah, they are disjoint, not disjoint. Second one is this one, na? Whatever I have written. Okay, I think just let me. My assumption is this is the second. Um, this is second, that X be a topological space and A and B collection of connected subsets. Okay, then A equals to A union. Then that will be connected if and only if there is the intersection is non-empty. Okay, I think you are saying this one, right? You are saying this.
Yes, sir.
So
Second one, sorry.
so second one will follow from the B. This is the correct. Okay, A need not be connected. For A, you can take like AN is connected 0, 1 open interval and 2, 3 open interval. Then A is equals to, this is A1, this is A2. Take A is equals to A1 of A2. This is equals to 0, 1 union 2, 3. So A is not connected here. This is not connected. This is not connected, and the second one will follow from that theorem, that finite theorem will follow from the, in general, that if there is a common point, then that will be connected. Okay, and that basically second one follow from the, for finite situation like union of A n, taken union of A n, that is not connected, that W1 disjoint union of W2. So as X is belongs to A n for all n belongs to natural number, so how it will be, so that this X will be in W1, right? But as A n are connected, so it must have an is subset of w1, and that is true for all n. Because why this will be? Because as an is connected and x belongs to w1, an should be in subset of w1. Why? Because if an is not subset of w1, that means there should exist a point y in an which is not in w1. That means this y is in w2. That means an can be written w1 intersection a1 union of w2 intersection a1, because this one is non-empty right now. So that means an is disconnected, but that is a contradiction because an are connected. So that's why this is the rough actually. So that this is for true for all n. That implies that wt is equals to 0 because all the an are contained in w1. So that means wt is necessarily 0. Okay. So this is, so b is correct, and similarly c will be correct. Similarly c will be correct. How? I think this is written even here also. You can take here new subset. This union of an can be written as union of bn, where bn is equals to union of an I equals to 1 to n. That is not a big deal. This is same actually. So c is also correct. Okay, so I'm not doing anymore. This c is correct and d false. Okay, I think clear this is right. Okay, yeah.
Sir, the third option should be like
Yeah.
an intersection an plus 1 is equals to 5 for all n.
Sorry.
Sir, in the C option, na?
C option is correct, na?
Sir, shouldn't be option be like that an intersection an plus 1 does not equal to 5 for all n?
Yeah, that is the condition. That is the condition given.
Sir, but here for all n is not written, na?
For all n.
Sir, I am saying here only two sets are disjoint.
No, not to see. This is true for all n. This should be true for all n. Okay, if you are asking that whether this is not written all n, that doesn't matter because this is symbolical. This is means that this is true for all n. Okay.
Okay, sir.
So
Okay, that's why I didn't take this
this is
option.
not that for single n. This is true for all n. Okay.
Okay, sir. Okay, got it.
Yeah. So that means we can first connect a1 to a2, and a1 union a2 is connected. Now a1 union a2 intersection a3, that is non-empty because a1 union a2, because a2 intersection a3 is non-empty. That means uh, just a minute. Okay, just let me. The point is that first a1 union a2, this is connected. Okay, now take this one union a3. This will be connected because a1 union a2 intersection a3, that is non-empty because there exists a point x which is contained in a2 and that is also contained in a3. Okay, in that this way you can say that ultimately full union will be connected. I don't know why it is not written. Yeah, I think this is clear. No? Yeah. So this is question number 3. Question number 3, that X be a topological space. If X is connected, then Xn is connected, and that is proved, I think. Right? It is proved that if X is connected, then Xn is connected. It is, I think, okay, Xn is connected. Yeah, that is proved in lecture 3. It is proved. It is written. It is proved, right?
Yes, sir. Already proved.
This is proved that X and Y are connected, then X cross Y is connected. Okay. So if x and y are connected, that means x cross y is connected. That means x to the power n is connected. And conversely, so converse is hold or not. Okay. So now converse is hold or not. That is given by projection. Let P be the projection. P be the projection. P maps from x1, x2, xn going to be the. I am taking P1 is the first projection. X1. Okay. First projection. Okay. So now what I want to show is that P1 is continuous. P1 is continuous. Okay, P1 is continuous because that is projection. As projections are continuous, P1 is continuous. Now what I need to prove is that X is connected. So for X is connected, that means I need to prove that inverse image. And okay, if I have, and P is okay, basically why X will be connected, P is, and X is actually image of, X is image of P1, image of X to the power n under P1, right? And if X from X to Y be an continuous function, this is giving for arbitrary continuous function, X is connected, then Fx is connected in Y, connected one Y with subspace topology. Subspace topology. Yeah.
Sir, F should be surjective as well.
No, that's why I'm taking that subspace topology. Fx is connected. So that
Okay,
means
okay, sir.
from
Sorry,
X to
sorry, sorry,
Fx
sir.
with subspace topology. Subspace topology, this is surjective, no?
Yes,
Yeah,
yes. Sorry,
same
sir.
thing,
Sorry.
same thing. This is same thing. What? You are correct. Exactly, you are correct. That if I write subjective, then we'll go. I think this is clear, na? So I don't need to write anything. Why this is? Because if f of y is not connected with the subspace topology, that means f of y can be written with the union of u union v to non-empty disjoint open set. Okay, now their inverse will be non-empty disjoint open set in X. So inverse F inverse U and F inverse B will be non-empty. That means that, and this X will be like F inverse U union of F inverse V. So that means we can write two non-empty disjoint open set of X, but X is connected, so that is a contradiction. Okay, I think that is the idea to proved in, hopefully improved in lecture note also. Okay, now question number 3 is done. Question number 4. Question number 4 is this. Yeah, this is the question number 4. Question number 4. What question number 4 says that which of the following sets are connected? Q cross Q with standard topology, X cross Y with X square, this is circle plus S line, and R minus 0, R square minus 0. Okay, so let's start with this. This is very interesting question, but first only one point. I think few years ago there was a questions in TIFR exam, either Q cross Q is path connected or not, or Q cross Q is connected or not, something like that question. But that is obviously related to this particular portion, that Q cross Q. Okay. So first fact is that Q, that means rational number, with subspace topology, that means as subset of the real number, subset of R, is not connected or disconnected, same thing. First of all, this fact is very important. Why Q is not connected? Because we know Q is equals to Q intersection real number, right? And that means this is equals to Q intersection minus infinity to infinity 2. Okay. Now take an irrational number C. For example, you can take root 2, pi, e, anything. Okay, C from real number, then C is not in rational numbers, that's natural. So rational number can be written Q intersection minus infinity to C union of C to infinity, right? So I can write Q intersection minus infinity to C union of Q intersection C to infinity. But minus infinity to C and C to infinity are open in real number. That means q intersection minus infinity to c and q intersection minus c to infinity are open in q with subspace topology. That means, and obviously also they are non-empty and disjoint. That means q is disconnected. This fact is clear. Is this fact clear that q
Yes,
is
sir.
why q is disconnected? Okay. If q is disconnected from the previous problem, that x is connected if and only this is the correct one. Okay. So this is the correct one, that x is connected if and only if x to the power n connected. So from that point we can say that q cross q is not connected. So this is cross. Okay. And second one is that this is not connected. Okay, now second one is that x square plus y square, that is unit ball, sorry, unit disk along with y equals to 1 subspace topology. Okay, clearly they are not subspace topology, that is connected or not. They are connected because they are path connected. Okay, why this is that I am just writing. So A is not true. Okay, so first take, this is the x axis, this is y axis, and let's write this one is the unit circle, and what it is written, that y equals to 1, that means parallel to x axis. This will be written y equals to 1. Oh no, sorry, this is, I think this is not connected. Y equals to 1, b is path connected and hence connected. Just 1 minute. This is the portion actually we have to remove this particular. This is not the full one. This is the actually the region inside this portion is x square minus, this is x square plus y square. Actually this is equals to all those xy coming from r square such that x square plus y square less than 1. This is the portion. And y equals to 1, I think, right? Xy and y equals to 1. uh, y equals to 1, I think. Yeah. uh, 0 comma 1, 0 comma 1, 1 comma 0. So this will be parallel to x-axis. Parallel to x-axis, yeah. Yeah, something like this. Okay. So this is something like x. This is something like x y belongs to r square such that y equals to 1. Okay. With subspace topology from r square. So this is connected or not. So question is that, so this is path connected. Basically, thing is that this is path connected. But why this is path connected? Okay, this is path connected. Mm. Okay, I think, I think I'll back to this particular example, whether this is path connected or not. I don't think this will be path connected. This is path connected, this is path connected, but if I take any point 0, 1, 0, 1 is there. Yeah, this is path connected. This is path connected. Why this is path connected? Because take any point. This is the point which is 0, 1, right? This is the point 0, 1. So we know that if A is connected, then A closure is also connected, right? Because if A closure is not connected, if I write A closure is equals to U union V or W1 union W2, this fact is clear. I think W1 union W2 and W1 and W2 are two open set in X, then A can be written as W1 intersection A union W2 intersection A. Okay, but A now obviously these are non-empty. Okay, as W1 and W2 are non-empty open subsets of A closure, that means they are non-empty. So that means they are non-empty. That means A will be disconnected. Okay, but point is that A is connected means A closure is connected. So here, what I want to show is that as this set X and Y belongs to R square, such that XY belongs to R is connected, then this set will be connected. X and Y belongs to R square such that XY belongs to R. Sorry, XY. What I am writing? X square plus Y square less than is equals to 1. So that means this is not less than equals to. This is just less than. This is connected. So X square plus Y square less than is equals to is connected. That means XY belongs to R square such that X square plus Y square less than 1 union of 0, 1 is connected. Path connected this is. All of them are path connected actually. As Atto is path connected and this is path connected is path connected. Now the set X and Y belongs to R square such that Y equals to 1 is also path connected. Now these two union is same as the XY belongs to R square such that X square plus Y square less than 1. This set union X and Y belongs to R square such that Y is equals to 1. This set is same as XY belongs to R square such that X square Y square less than 1 union 0, 1 union XY belongs to R square such that Y is equals to 1. These two set are path. This I can write these two union, but this set, particularly this full first two, this is main. Basically, I want to say is that this set is path connected and this set is path connected. So their union will be path connected because there is a common point. What that common point? That is 0, 1. This is the common point of this set and this set. Okay. So that means having common point, that will be path connected. And as this is path connected, this is path connected. So this is path connected. So connected. So B is true. So what we have seen is that A is false, B is true, and C is not connected. Why C is not connected? That is very much easy. Why C is not connected? R minus 0. This set is nothing but minus infinity to 0 union 0 to infinity. So this is not connected, clearly not connected, because that is union of two disjoint non-empty open set, not connected. And D is R square minus 0 point. and this is connected, this is path connected, so connected. Why this is path connected? So connected. Why this is path connected? Because you can look at the graph actually. Suppose this is x-axis and this is y-axis. Now just remove the point from here. Just remove the, this is the full plane. Full plane. Just remove the point from here. This is the point. Just removing the point. This is the point. Removing the point. This one and all other pointers there. But whatever, what doesn't matter. Take one point and you want to connect a path from one point to other. So if these 2 points are, if these 2 point A and B are on the line, online which contains this particular point origin, so you can take third point C, you can join a line from A to C and join a line from B to C, so you will get a path from A to B. For any two arbitrary point A and B, you will get a path from A to B. How? If the line joining, first try to find the path joining A to B. Try to find the line joining A to B. If that contains the infinity, that contains the origin, this particular point origin, then try to find another point and connect like this way. And you know that how to find a path. That is basically suppose I have 2 point, I have 2 point like x and y. I want to connect a path. What will be the path? That is tx plus 1 minus ty, and that is the path. That is basically this is the path. That consider gamma is a function 0 1 to the space x. How this is? Gamma t is equals to 0 t, sorry, at xt plus 1 minus ty. If this gamma t contains the point 0, then you have to use third point C. If that does not contain 0, you can just take the direct line. For example, if I want to find the path from A to C, why I will take another third point? Directly I can connect here. Okay, this is D. Okay, so that means this is path connected. Okay, so what happens that this R is actually connected. Okay, I think this is clear now. If there is any problem, please raise. I don't have any issue to repeatedly. Uh, okay, I think there is another problem 5 which I have not. I think I don't have picture, so I'm writing the 5 actually. Problem number 5. What 5 says is that any connected component of a topological space is open. First of all, answer A, B, true or false, and this is clearly false. You can just take.
Sir, this was proved in a lecture actually.
Yeah, that is not. Yeah, I am not going to do this. I'm just saying this is not even connected component of a top component. When this is component, that is proved in general, that any connected component that will be closed. I think, right? If I'm not wrong, path connected, not
Yes,
path
sir.
connected.
Yes,
Connected
yes, sir.
component are closed. So if it is written closed, then it should be true. But it is open, then false. But if it is
Yes,
written
sir.
that it can be closed and open, but that will be false again, because it always open closed. It can't be open for path connect. Sorry, for connected. Yes, okay. Okay. Now problem 6. Problem 6 connected. This one. Yeah. This is the problem 6. I think this is problem 6. Problem 6 says that if let P1, TP2, P are, okay, two things. Here, note that two things. One is that note that R is always greater than 1. N positive or not, R is greater than. That means this particular thing, P1, P2, PR, that should contain at least 2 point, P1, P2, at least. Okay, and this should contain at least P1, P2. Now question is that let P1, P2, PR finitely many points in the sphere, on the sphere Sn, choose the correct option. That first question is that Sn minus P1, P2, PR is, Sn means, you know, the Sn means actually R to the all those are coming. And just to recall, Sn that is equals to Sn is power Sn. Sn that is equals to x1, x2, xn plus 1. Okay, that is coming from Rn plus 1, such that summation of xi square is equals to 1, I equals to 1 to n plus 1. Why it is writing Sn? Because using this particular thing, one dimensional is can be dropped. That is the thing. Okay, this is coming from, this is subset of R to the power n plus 1, and that is n plus 1 dimensional space. But using this particular equation, that circle sphere equation or circle equation, so we can drop one dimension. That's why it is written Sn. Okay, now point is that here R is always greater than 1, so P1, P2, Pn will contain at least 1 point. Here I will do the sketch actually, not the full proof, because that I have to write many things. So that's why but if it is not clear to you, then I will write again. Okay. The fact is that um, the stereographic projection Sn minus P1, that is north pole. If I take right north pole, I think that exact statement I think is written here. Huh. Sn minus 1, this is north pole, is homeomorphic to R to the power n, right? This is proved. That is how it is proved. That is basically, take, this is the x-axis, not x-axis, something like, for three-dimensional case, this will be something like, this is x, this is one axis, this is other axis, and this is third axis basically. And so taking like some sphere, and this is the north pole, except this pole, connect any point of this sphere and join this point and extend the line, that will be, that will that will give a image on this plane, particularly on this plane. Okay, this plane actually, this is the plane. So this is third dimensional. It is not easy to write in two dimensional. So I think you will understand. Not a big problem. So this is the projection. So we can give a map from this point to this point. For every point on the sphere, I can connect that point with the north pole point and extend it, and that will cut the point. That will cut the cut the this particular plane, and that will give a projection. Okay, so that will give a map. That is the stereographic projection actually. Okay. So for stereographic projection is homeomorphism actually, from Sn minus 1 to real number. Okay, this is for real number, R to the power n. Not this one is this particularly. Okay. Now what I want to show here is that as R to the power n minus a single point, this is homeomorphism. As R to the power n minus finite number of point, but okay, make sure that this n is positive, n is greater than 1. Okay, yes, Vivek. Vivek, is there any question? Okay, sorry. No, use the fact that okay. So when n is greater than 1, when n is, if n is 2, sorry, if n is 1, if n is 1, then that will be like S1. S1 is circle. S1 is circle, and take the north pole and okay. Yeah, Vivek.
So I guess this was already proved in one of sir's lecture that Sn minus
Finite number
finite
of,
points is homeomorphic to Rn.
yeah, yeah. Actually, that finite point doesn't matter. Actually, I mean that is path connected. For example, this one finite connected point will be homeomorphic to Rn, so that will be. But I think that in that situation we need n greater than one. That is what my point is there. Because why n greater than 1? Yeah, that is same thing, sorry. Main point is that we know, the fact is that we know, and another fact that is we know r to the power n minus 0, or a single point, or a finite number of point, finite number of point is connected if and only if n is greater than 1. That is what I want to make. Yeah, that is the point. That means r minus, if I take r minus 1 point, this is not connected. But r minus a point is connected. That is what we have seen few minutes ago, right? Okay. So
Yes,
here,
sir.
yeah, here it is that r is always greater than 1. Okay. Now, if that means I am taking a minimum 2 point here. Okay. And Sn minus n is subtracting one single point. So that means if I subtract another point with this one, another point is um, something like ax or some particular p. Yeah, p. I can take p. This p, then that is homeomorphic to the single point Rn minus that particular, the image of the point P. Got it? Right. So from here, from Sn, subtracting R point is similar subtracting R minus 1 point from R to the power n. Okay. So this is so that means Sn is connected, Sn minus P1 PR is connected if and only if r to the power n minus, here it will be like r to the power n minus r minus 1 point is connected, r minus 1 point is connected, this set r minus 1 point, this set is connected, this is the point. But r is greater than 1, so r minus 1 is positive, integer, so r to the power n minus r minus 1 point, this set is connected if and only if n is greater than 1. Okay, so that's why only if n greater than 1 connected, n greater than 0 is not correct, and not connected is false, because I can take n greater than 1, n greater than 2, and connected only if n equals to 1. That is also false. Is it clear? Main funda is that from stereographic projection, I mean from sphere, if I subtract 1 point, I will get r to the power n. If I subtract 2 point, I will get r to the power n minus single point. Okay, because there is homeomorphism, that means there is a bijection. If I remove 1 point, that will be removed from the, maybe something like this way. I'm just, this is something like rough, I can say. I'm not writing this is some full school. You have to write it from stereographic projection, and taking r equals to t, you have to prove this one, and other will automatically follow. I'm just giving idea. Okay, this is the idea basically. Okay, so from r to the power n, if I subtract r minus 1 point, and r minus 1 is greater than, r minus 1 is always some integer, positive integer. So that means that will be connected only when n is greater than 1. If n is equals to 1, that will not be connected. But for other n, other positive integer, it will be connected. Okay. Okay, I think this is clear. 6. Now I need 7. Okay, here I will stop the presentation for 2 minutes. 1 minute. Just a minute. I need to get those picture where I don't know. Up to 6 is done. I need 7. Eight, 9, 10, 11, 12, 13. Yeah, thanks. Just a minute. Okay, I think there is a network issue. Just, yeah, just one more minute. I don't know what is happening. Just little technical problem. 1 minute. Okay. Next problem is any path connected. If I'm not wrong. Any path connected. This is the thing. Okay. Question is that any path connected component of topological space is closed or not? Okay. The answer is false. False. Why this is saying false? You can any path. Question is that any path connected component of a topological space is closed. This is true or false? Maybe open, maybe closed. Yeah, correct. Yeah, maybe open, maybe closed, maybe not necessarily uh, open closed. Okay, not necessarily open or closed. Yeah, but in subspace topology it will be closed. Yeah, maybe not open. Yeah, you can write the example. I think sir already gave an example that you can take that example. What is that example? This one. That example is I think set is that one set is 0 y, not 0 y, such that y is coming from less than 1. This one is the one set union uh, n 1 by n. N is coming from the natural number. This set union x comma 0 such that 0 less than x less than is equals to 1. So that means suppose Suppose this is the x-axis, okay, and this is the y-axis. I think this is the y-axis. I think this line, yeah, this is y-axis, and just removing this point, actually removing this point, that is the what the main point is. That why this removing point is very important. What the, I mean, even that whatever I am doing here, that will also help why path connected component need not be path connected. That is what here. What is that? From is that, suppose this is the you can look this, except this point, the whole, except this whole, this set, the point on this line is actually corresponding this set, right? And if this is 1, then point except this whole point on this line is corresponding this set. Okay, now if I take this set, particularly n comma 1 by n, when n is equals to 1, this n comma 1 by n is actually n comma y. I think that is false. N comma y, n comma y, not n comma 1 by n comma y. Y is actually here, y is 0 less than is equals to 1. That is what? Or 0 less than y less than 1, I can take, that is not a problem. Okay, so this is the point where n is equals to 1 and y is actually this set. Okay, now when n is half, this is the point, n equals to half, this is the point, and y will be that means the next line will be like this way. Okay, this is, then next line will be like half of this, and next line will be like half of this, and next line will be like half half of this. In this way we will be able to get the lines in this direction, but we will be able to get the line in this direction. Okay, so if I take two portion, one portion is like this portion, one portion is like this portion is path connected, because take any point here, any point here, you will get able to get the path from this way, right? Take any point here, any point here, you will able to get the path from here to here to here. So this portion is path connected, this is path connected. But the full thing, this is also path connected, but the full thing is not connected. Okay, but this path connected component, what is called, that is, if I write, so this path connected component basically, what is that all those point n comma y, n belongs to natural number and y is coming from 0 less than y, this set union x comma 0 such that 0 less than x less than is equals to y, not 0, 0 should not be in the point. This set is path connected, that we have seen, right? But not closed. Why this is not closed? Because if you look at the diagram, actually what the diagram we are trying to draw here, the point is coming from whatever the point on the y-axis, they are limit point of some point, of some sequence, right? I can construct a sequence of which they are limit point, but uh, okay, sorry, this is the mistake I'm doing. This is 1 by n, 1 by n, this is the 1 by n. Yeah, so this is the point. So every point on the y-axis, they are limit point of some sequence coming from this particular set, this set. Okay, but those are point is not in this set. This is the set of which the limit point. Okay, I don't know why it is not okay. Is it clear? I hope so. I don't
Yes, sir,
know.
got it.
Ah, okay. I think my screen is not smooth, right? It is getting freeze.
No, sir, it looks fine.
Oh, okay, okay, thanks. I think this, I don't know why it is showing me that it is not smooth. Like, I mean, whatever. Okay. Now I need 8. What 8 problem it says is that any connected space is path connected. I think that is. I will not write that one. This is taking space. The problem number 8 says that any path, any. This is no need to write, any connected space is path connected. This is false. Why this is false? Any connected space is path connected. Why this is false? This is standard. I don't need to write anything. Okay. 9. 9, I will not even copy the question from here. I'll write here. What 9 says is that S1, which is the spare actually, sorry, unit circle actually. S1 is homeomorphic to 0, 1, close interval. Option A, true. Option B, false. The answer is false. It can't be true. Why? Because if S1 is homeomorphic to, I think this is given here. Okay, we know if this is okay, just I'll explain that one only. If A from S1 to 0, 1, what S1 is basically, this is all those xy belongs to R square such that x square plus y square is equals to 1. This is, if S1 to 0, 1 is homeomorphic exists, homeomorphism, if there exists if a homeomorphism is a homeomorphism, then okay, I think in reverse direction it is written. Okay, sorry. If there exists an homomorphism f from 0, 1 to s, then f restricted to 0, 1 open interval, that will be 0, 1 to s minus f0, f1 is the homeomorphism, right? We have the homomorphism this way because homomorphism is bijection map, right? So now 0, 1 is connected. So f restriction to 0, 1, this map with image, this should be connected. But this is actually equals to s minus f0, f1. But this is actually equals to something like r minus a single point, a point, right? Because s minus 1 point is r, s minus 2 point is r minus a single point, not connected. But r minus a single point is not connected, right? And also we have looked at sees from the previous theorem, that previous some exercise, that s1 minus p1 p2 is connected only if n greater than 1, right? If it contains 2 points. Okay, so this is the thing. Now problem number 10, that I will also not copy the questions. What is that? If x and y are path connected, yes Vivek.
Sir, if S1 was a part of R square or R to the power n, then it would be a homomorphism.
Sorry, 1 second please.
Sir,
1 second.
if we are talking about S1 here, na?
S1,
If instead of S1, it would be a sphere in Rn.
sorry, instead of S1, if I write spare of Rn, okay, s to the power n minus, that way.
Yes. Then
No,
will it be homeomorphic or not?
yeah, but there it will not be there is the problem, okay, there. So yeah, I mean you are saying that instead of S1, one thing, this Sn minus arbitrary finite number of points, which contains more than 1 point, even 1 point, but that should contains at least 1 point. Okay, so this set is actually this set is connected, path connected, right? Because the fact is that r minus 0 is not connected, but r square minus finite number of set is connected. Got it? But there is nothing like interval also, na? In r to the power n, there is nothing like interval also. Is there any interval? We can write it box,
Hmm?
rectangle, those things, r to the power n. but there is nothing like interval.
Yes, sir.
Here,
There is no interval.
yeah, here is the fact is that this particular 0 1 closed interval 0 1, because this is closed connected. Okay, there if you write something like minus, I mean something like a cross b, a cross ab cross cd to open interval, something like, then that will be connected, that will be connected, and the image will be, so there will not be even exist, yeah, that we can, so if I mean question is something like we can say whether this set, yeah, there is the point. Okay, let me, I think this is very interesting. Okay, just remove this point. Suppose you are asking for these questions in general setup, in two-dimensional or three-dimensional setup, right? So for example, this interval will be
Yes,
replacement
sir.
of something like AB cross CD, close interval. This one will be go to A square minus A square. Whether the question is whether there exists an homeomorphism like this or not, right?
Yes, sir.
Whether there exists any homeomorphism F, right? This is the question. Clearly, if you look at the diagram, if you look at the diagram means x-axis and y-axis. Suppose x-axis, this is A, comma B, and this is C, comma D. So this is the region which is actually, this is the region which is actually A comma B close interval. This is close interval, not open. This is close interval cross C comma D close interval. So this will be like a closed rectangle, means with boundary, right? Now if I want to give the map from here to here, so like previous map, if I want to do like if I restrict it something like A comma B cross C comma D, neglecting the end point, that is what I have done there, right? So this will be the map from A comma B cross C comma D. This is means open interval cross open interval. Then in that situation, what and S2. Here what I need to subtract, did you know what I need to subtract here to give the homeomorphism? Here I need to subtract infinite number of points, uncountable number of points, not only infinite. I mean, for example, what previous I have done, that F is a map from AB to S1. I want to restrict it from AB to S1 minus FA, comma FB. This map defined by the previous one will be homeomorphism, right? But similarly, if I subtract here the point, actually what is the point is that whenever I will take an interval, there is two endpoint only. Okay, I can remove that endpoint and get something like this. But whenever I have rectangle in two dimension with the boundary this, and if I want to remove the boundary point, I have to remove this boundary, this red region portion, which contains infinite number of point. So it will be like, then if I want to get the homeomorphism F from AB cross CD to some space related to S2, then that will be S2 minus infinite number of points. What the infinite number of points? Like A comma X, where X can be any point from C to D, and F of B comma X. Similarly, F of X comma C, F of X comma D, X, something like this, and that will be uncountable number of points. Did you got what I want to point out? So we will not have S2 minus or SR minus finite number of points. We will have SR minus infinite number of points, and then we don't know whether that is connected or not. Is it clear
Yes,
what I
sir.
want?
Understood it now.
Yeah. So I mean, in that situation, only subtracting 2 points. But if I go to in higher dimension and do the same, then I will have to subtract infinite number of points, and then I don't know, because then I don't know whether this S n minus infinite number of point, uncounted number of point, that is connected or not connected. That we don't know. I mean, something like if you imagine a sphere, and that sphere, if you just cut a line, for example, if you have a sphere like ball, if you have a ball, football or something, if you remove a line or draw a line, just draw a black line or not full line, half line. That half line contains uncountable number of points. But if you remove that black line, point on the black line, then still it will be connected. Every point on the ball will be connected. But if you do the line as the full circle, I mean full whole circle all around the ball, and if you remove that point, then that will be disconnected. So in every situation we are removing infinite uncountable number of points, but in one situation we are getting connected, in one situation we are getting disconnected. Okay, I hope it is clear. Yeah. This will be like here it will be infinite number of points. Infinite number of points. Okay. Okay, I think this is 10 is done. Now main target is that next 40 minutes we have to do these five questions related to the path connected and connected of matrix. I think that is very interesting questions. Those are 11. Question number 11. Yeah, this is the question number 11. Okay. What question number 11 says that which of the following subsets of R to R square are path connected? First of all, A is path connected. Why it is path connected? Set of lines, but there is a common point. That common point is 0, 0. That's the reason. Union of n equals to 1 to infinity xy such that r square x is equals to ny, n is integer. This is equals to union of an, where an is equals to all point x comma ny. X and y are coming from, yes, all go through origin. Yeah, that is, I mean, I'll draw a diagram also, union of all n, and note that 0 comma 0 is an for all n. So basically basic fact is that this is the x axis, this is y axis, and this is y axis. What is the thing is that I'm drawing all in something like this way. All are coming going through zero line. Okay, so any point I can take here and here. I want to connect those 2 points. I will connect through 0. This is the line. Okay, so this is the connectedness. I will get the path. Basically, that is the thing. B. What B says is that xy belongs to R square such that xy is equals to 1 union xy belongs to R square such that y is equals to 0. Okay, so question is that whether this is connected or not. Just let me first draw the line. What xy equals to 1 and y equals to 0. Y equals to 0 means x-axis, right? Xy equals to 1 means something like this way. No path connected since no common points. Yeah, that is correct. So that's why, that is the reason. So not path, no path. These two set are not connected, but I have to give some concrete reason. That is what this is the line. Okay, I think better to write. This is the x is equals to y. This is xy equals to 1 and y equals to 0 means this is x-axis. X-axis is the y equals to 0. Y equals to 0. I have to show there is no path actually. That is the thing. I will, if there is any, the set B is not connected. That is correct. Yeah, I think why it is not connected. I just want to give some very concrete type of concrete example. This is not connected. That is what my claim, right? Not connected. Claim not connected because is not connected. Okay, what Vivek? I think there is a one problem. You said not path connected since no common points. Yeah, not path connected, but not path connected implies that does not imply that that is not connected, right? It can be not path connected, but still it is connected. Yeah. So we have to make sure that it is not path connected. That does not imply that this is not connected. Okay. Okay. It can be connected. Okay, so that's why you have to show that not connected. So that means I have to what I have to give that it is disjoint union of two open set. That is the what I want to say. Okay, that I got I think. Y equals to 0. This is one open set. Another open set is got it. Let's why it is not connected. Now let's S is equals to let X is equals to this is the set whatever the set. Yeah, these two sets can be used as A and B which are disjoint. Right. That is what I will prove. That is what. So x is equals to xy coming from r square such that xy is equals to 1 union of xy belongs to r square such that y equals to 0. Now what I will prove this is the set S that is union of two sets but I have to show that they are I have to show that x with subspace topology of r square, right? This is the what we but note that x intersection all those xy coming from r square such that xy is equals to 1 sorry xy this is greater than 0 x intersection xy greater than 0 this set is nothing but xy belongs to r square such that xy is equals to 1, right? Yeah, I think x intersection sorry I think okay, let's write it clearly. uh, Here x intersection xy coming from r square such that xy product is greater than 0. This is as a subset r square and open in r square, right? And this is equals to actually all those xy belongs to r square such that xy is equals to 1, right? So this is open in x, right, with subspace topology. Clear? What I want to say is that x with intersection of an open set coming from R square is this set, right? That means what are the general open set? General open set of a subspace is that X intersection a standard open set. This is a standard open set, and that it makes intersection with X and that set. This set will be open in X. Okay, I think this is clear. And this is also closed in, and this set also this set is closed in X. Why this set is closed in X? As X intersection this one exactly subset of xy not is equals to 0 this set. Yeah, xy not is equals to 0 is actually this set, and this is closed subset in R square. Subset in R square. So what I proved that this set, particularly this first component actually this set, what I want to prove is that this set is actually open and closed in the subspace topology of this set. How this is happening? Because this set is intersection with an open set of R square, and this set is intersection with a closed set. This is open set and this set is intersection with a closed set of R square, right? So that means this is open and closed as well as. So that means, and that is, I think, if you remember that in standard topology, I have a topological space, and if I take subset, in that subset and subspace topology, open set will be nothing but intersection with the open set full space X with the intersection of open sets of the main space, and closed sets are similarly intersection with the closed sets. So that is why this is closed and open. So that means this set xy belongs to R square such that xy is equals to 1 is closed and open in X and non-empty. But if you remember the first definition of the disconnected, that if a set contains, if a topological space contains a non-empty set which is open and closed both, non-empty trivial set, okay, sorry, non-empty proper. This is non-empty and proper subset of, this is non-empty and proper subset of X. So by definition, X is not connected, right? Disconnected basically. X is disconnected. This is the first thing. Second thing, the C option says that all those point X sin X. Okay, option B is clear, na? Option B is, I'm just proving very easily.
Yes, sir.
That is just intersection
Yes,
with an
sir.
open set. Sin X, okay, X sin 1 by X. X belongs to 0 infinity union of 0 0. Okay, what I want to say is that, okay, this is question is that, okay, whether this is connected or not, that is, I mean, C option, this is connected or not. So what we have seen is that this is not connected, right? This is connected, and we will prove that this is not connected. And so I think option A is only correct, and D is correct. D is correct. Why D is correct? Oh, that is coming from the standard topology. Okay, that is coming from a very interesting lemma. That I will, sorry, interesting exercise. Okay, from here, whether this is connected or not. This is the question. Connected or not. This is the question. Why, whether this is x comma 1 sine 1 by x is connected or not. That is the question. Okay. But not only x comma sine 1 by x. Did you know what x comma sine 1 by x graph looks like in R2? This is the graph. Yeah. So graph is something like this will be something like very much engaged here actually. This is something like this, but this will continue this way, like, okay. So what is the important point is that it will be very much near to the y-axis. Okay, very much near to the y-axis, but that will not touch to y-axis. So that's why this set, interesting fact is that this set is path connected, because this is the path actually. This is the path what I have drawn. So that means for any 2 point I will have the path actually, right? So that means this set is path connected, but what we will prove that this set with this point 0 comma 0 is not path connected. Okay, not path connected. Prove that, and prove that there is no path joining 0 1 or not. Oh, okay. Sorry. Question is here whether it is path connected or not. Yeah, question is here path connected or not. This is not. Okay, I think I have written wrong thing here. So by definition, X is not path connected. Sorry, X is not connected. So not path connected. Not path connected. Okay, so you were saying from directly. Question was path connected or not. Okay, sorry. I was reading connected or not. Okay, is path connected or not? This is path connected. This is connected actually. Is path connected or not? So that this set, this without 0 0, this set is path connected, but 0, if I add 0 0, that will not be path connected. So what I will show is that we will show there exists no path. We will show there exists no continuous function gamma from 0 1 to the set x. I'll write this one as x, such that gamma of 0 is equals to 0 comma 0 and gamma of 1 is equals to 1 comma sine 1. Can we use same logic? That means A union B, and here A or B disjoint. Oh, okay, you are saying asking for previous one. No, no, no. Here A or B disjoint, yeah, you can use. But how you will show that A or B disjoint here? You can use. But here I don't think this disjointness is here. It is in B, option B. What I have proved is that there exists a set which is both open and closed and not empty and proper. That means that is the definition of disconnectedness. So that is disconnected. So that where if this is disconnected, so this can't be path connected, because if it is path connected, that should be the connected. So that's why this is not path connected. Here question is that this X set is connected or not. Okay, with 0, this set is connected but not path connected. So you will not be able to give disjoint set. Did you understand what I have said? Here option C, that x comma sine 1 by x union 0 0. This set is path, this is connected but not path connected. Okay.
Yes, sir. Got it. Got it.
So that's why you will not be able to give here disjoint set. I mean, if you want to prove that this is not connected, so you will not be able, because this is connected, but this is not path connected. That is what we are proving here. We will show that there exists no continuous function gamma from 0 1. So we will show there is no path joining these 2 points 0 0 and 1 comma sine 1. These 2 points. These 2 point 1 comma sine 1 is coming from the first component, main component. 0 0 is separate component. So my point claim is that this is not connected. There is no continuous function like this way. Okay, I will try to rapidly, because this is very little big problem. Okay, suppose there is such continuous function. We will prove contradiction. Suppose there is a continuous function gamma from 0 1 to x, such that gamma of 0 is equals to 0 comma 0, gamma of 1 is equals to sine 1, but gamma is equals to gamma 1 comma gamma 2, where gamma 1 is equals to, gamma 1 is a map, gamma 1 from 0 comma 1 to the real number, and gamma 2 0 comma 1 to real number, because that is x is a subset of R square, where or continuous, where gamma 1 of 0 is 0, gamma 1 of 1 is equals to 1, gamma 2 of 0 is equals to 0, gamma 2 of 1 is equals to sine 1. Okay, actually that is coming from projection actually. Okay, I don't need to write here. I think better to write there projection, using projection. That will be better. Not, I mean, that will be more correct, because here full space is not. Okay. So my first point is that I want to prove is that there is no continuous path actually. Okay. Okay. Now take this is the set. Now take S is equals to all those x, all those t belongs to 0 1, all those t belongs to 0 1, such that gamma t is equals to 0 0. Clearly, this set I am considering set, clearly 0 comma 0 is in S. That means S is non-empty. Take A is equals to supremum of the element coming from A. C belongs to S. C. Then C belongs to S. Supremum C belongs to S. Then there exists a sequence Cn coming from S, such that Cn, here it is in metric space, Cn will converge to C. That is even not a problem. This is in 0 1. This is I am talking about exactly in 0 1. Cn, all these things are coming from 0 1. So there is a matrix. C1 converges to C. And gamma being continuous, gamma of Cn will converge to gamma of C, but Cn is coming from S, and then gamma Cn is equals to 0. That means gamma C is equals to 0 because Cn is coming from S, and S is the collection of all those points where gamma T is equals to 0, 0. This gamma C is actually basically, this is the point 0, 0, right? Gamma C is equals to 0, 0. Okay, let's just check whether recording is on or not. The recording is going on. Okay, gamma C is 0, 0. Let and okay, so that means not C. There is, I want to say, there is, this is A is the supremum, so this is the A. This is A. This is A. So gamma of A is equals to 0, 0, right? Now now let P1 and P2 are same thing. I'm talking P1, P2 are R square to R is projection. Then gamma is equals to L, gamma 1, gamma 2, where gamma 1 is equals to basically P1 compose gamma, gamma 2 is equals to P2 compose gamma. Basically, what the thing is that this gamma 1, gamma 2 is nothing but gamma is a function from 0, 1 to x, right? This x is r square. That means gamma of any element will give two element gamma 0, gamma 2, 0, something like this way. Okay, so this is the what I have written few minutes ago. That is the thing gamma 1 and gamma 2. Okay, this is the same thing where gamma 1 of 0 is equals to 0, and um, gamma 1 of 1 is equals to 1, and gamma 2 of 0 is equals to 0, gamma 2 of 1 is equals to sine 1. But along with, look at one thing, gamma of A is equals to 0. That means gamma 1 of A is 0, and gamma 1 of A, gamma 2 of A is 0, right? But we don't know what gamma 1 A and gamma 2 A is. But what we know that gamma 1 and gamma 2 are continuous individually, are continuous. Okay, this is, I think this is very much clear. Now what I will prove that, that means gamma 2 is continuous at A, then for epsilon equals to 1 by 2, there should exist a delta greater than 0 such that, and delta is very small, at least I am taking very small, sufficiently small such that A minus delta is in, I mean, such that whenever x minus A, or t minus A, not x, t minus A is less than delta, mod of gamma 2 T minus gamma 2 of A is less than half. This is the epsilon. Here delta is chosen in such a way that A minus delta, sorry, T minus delta, or basically distance from A to delta, this distance is less than 1, basically. Yeah, that is what I want mean. This A minus delta is less than 1, or basically delta is such that very small, such that this is the, suppose this is 0, this is 1, this is point A, delta should be smaller than this distance. That is what I want to mean. Okay, this is what I want to mean. Delta small means this 0, 1 is there, A is there. I want to took delta in such a way that 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 distance from delta, and delta should be in between this way. I mean, this 0 and 1 distance. Okay, so this is some different thing. Okay, so this will be this way. So, but gamma 2 A is actually 0. That is what we have seen. That means gamma 2 T is mod is less than 1 by 2. Okay, that is what one fact is there. Okay, I will not touch this one. Okay, now sine 1 by x is a function with the property for any t positive sine 1 by x maps 0 to t, this closed interval or this open interval, closed interval does not 0 t, 0 except t, to onto maps this one onto minus 1 to 1. What I have said, sine 1 by x is a function of x such that whatever t I can choose, that should be positive. However small, however large, that doesn't matter. 0 to t, this interval will be mapped to -1 to 1. Why? If you look at the graph here, whatever graph I have drawn few minutes ago, there as much as we approach near to 0, still the function is taking something like this is oscillating from -1 to 1. Whatever small interval, whatever small delta I can choose, or whether how much nearer to I go to 0, this function will oscillate to 0. I mean oscillate from -1 to 1. That means it will take every value from -1. I mean the point is that here point what I want to make is that suppose this is the sine 1 by 1 curve. Here is that whatever how small I can take the portion here, how small I can take portion here, in that portion, in that particular distance of x-axis, it will take oscillate from -1 to 1. That is what I want to mean. Okay, is it clear what I just said? So that's why. So I want to make this. Want to say that 0 to 2 t maps -1 to 1. So it will take every value of sine x. So that is -1 to 2. So that means there exists an x naught. Okay, so sine 1 by x maps 0 comma delta gamma 2 0 comma gamma 1 of gamma 1 of a plus delta. This means whenever for all t a less than t less than a plus delta. This is the thing, because left hand side it is already 0 for all the gamma 1 maps this set onto -1 to 1. That means there exists a point x naught from 0 to gamma 1 of a plus delta such that gamma 2 of this x naught is equals to sine x naught. Gamma 2 x naught is equals to sine is equals to this will it will take -1 to 1 every value. I can take 1 here. It will take -1. That means gamma 2 of x2 means that is sine x function basically. Yeah, this is the thing. Gamma 2 of x2 will be x naught will be 1. That is what I want to mean. And gamma 2x is actually sine x function here. Right? Yeah, I think this is correct. It will take value -1. That is what I want to make sure. Okay. But this gamma 1 is continuous and x naught belongs to 0 to gamma 1 of a plus delta, and gamma 1 of a that is already 0. Okay, because that is what I have written here. Gamma 1 of a is 0. So gamma 1 of a plus delta, and gamma 1 is continuous. That means by intermediate value property of gamma 1 continuous function, there exists a point a which is a t which is less than a plus delta a to a plus, such that gamma 1 of t is equals to x naught and gamma 2 of x naught uh, is equals to 1. That means no, so this is not gamma 2 of x naught. This will be like not gamma 2. This will be like sine of 1 by x naught is equals to 1. So that means this is not gamma 2 of, that means there exists a t that gamma 2 of this second portion which is equals to sine of 1 by gamma 1 t which is equals to sine 1 by x naught which is equals to 1. Okay, but what we have proved that, so that means there exists a t from a to a plus delta such that gamma 2 of t is equals to 1. But we have proved that gamma 2 of t is always less than half just few minutes ago. This one, gamma 2 of t is less than half. So that means So that contradicts to the fact that contradicts to the fact that gamma 2 of t is less than half. So there does not exist any such continuous function or continuous path connecting 0 comma 0 and 1 comma sine 1. So x is not path connected. Clear? So I think it is. If it is not clear, you just try to read and ask me. Then, if it is not clear, you can ask later. I think right now I don't have much time. A long path taken to prove disconnected. Yeah, disconnectedness. Actually, not disconnectedness. Here, what I have proved is that there does not exist a continuous path. That is what. But that is used too many things. You just try to understand this. If it is not clear, in somehow I'll try to understand or try to write LaTeX if it is not clear after reading. Then I think that will be clear. Okay. And the second one I'll prove later. Just claim is that r square. What is the second option is that is I'll write that is last option. That is what the last option is that r square minus q less than. This is connected. Path connected, not connected, path connected. This is path connected. Yeah, you if I understand it or not. It means yeah. I'm This is path connected I'm writing. If I get time, I'll back. Otherwise I'll not prove right now. Okay. This is nothing. You can even get somewhere that if that whatever hint is there, that if A and B are two subset of x and y respectively, and x and y are connected, then x minus sorry x. Okay, I'll just give a hint here, not more general hint. For any for any let x and y not let x and y are connected, okay, and a and b are proper subsets of x and y respectively, okay, x and y respectively, then x cross y minus a cross b is connected. Okay, that is what I want to prove, right? So what we can write hint, I'll hint is something like here, whatever hint will be, that will be more or less. You just need to check all those things. I'll write and you just need to check all those things. This a cross b, this is equals to, I'll write x minus a cross y union of x minus a. Okay, we uh, try to do fast. See if I want to do fast here. I think x has two path connected, x connected, then x y with proper topology path connected. Okay, just a minute there. Okay, no, that is me. No, I think then I have to write this here. Uh, all those, yeah. This will be union of two type of union will be there. First union is u ux open set cross just a minute. 1 minute, just 1 minute. Yeah, I think it will be able to write the union of something like um, ux union of all y coming from y minus b. Okay, I'll write in. Not I will not. I'll write later. Okay, this will be claim. I'll just write later. Okay, not problem. Not a problem. Okay, I'll try to do other problem. Okay, 11. 11 is done. 12. 12. What 12 says is that this is 12. I think, right? Yeah. Okay, 12. Before starting 12, I'll write one interesting uh, fact here, and this interesting fact will help to prove not only 12 but all other problem after this. Okay, what is that? Let x and y are two topological space. Okay, topological space, and x has two connected component or path connected component. X has two uh, path connected component, and y has three path connected connected component. So let's there x1 and x2, and here y1, y2 and y3. That means what I can write, x is equals to x1 union x2, and y is equals to y1 union y2 union y3, right? Now x cross y has product topology, and x cross y, which will be like x1 union x2 cross y1 union y2 union y3. This one check that this will be like x1 cross y1 union x1 cross y2 union x1 cross y3. This this is cross means this is a tuple, that means this is tuple. X1 cross y3 union x2 cross y1 union x2 cross y2 union x2 cross y3. These are the set. Okay, and these are all of them. You can look at these two set. This set is connected, because why this is connected? Each of the component are connected. Each of these constitute functions. Each of these 1 2 3 5 6 3 4 5 6. Each of these six subsets are connected. Subsets xi cross yj, xi cross yj, I equals to 1 2, j is equals to 1 2 3 are connected. Why they are connected? Because are path connected, not only connected, they are path connected. Are path connected. Let's revisit once that what I have taken, x equals to x1 union x2 and y equals to y1 1 union y2 union y3. And x1 and x2 are path connected component, y1 y2 y3 are path connected component. Now x cross y has product topology. Okay. Now x1 and union x1 y1, these two as a subspace, they are path connected. So their product will be path connected because there is a theorem that as the product of path connected set, as product of path connected space is again path connected, right? Path connected. So as x1 is path connected, y1 is path connected, x1 cross y1 will be path connected. Similarly, x1 cross y2 will be path connected. Similarly, x1 cross y3 will be path connected. Similarly, x2 cross y1 will be, x2 cross y2 will be, and x2 cross y3 will be path connected. But you can note that x1 comma y1 and x1 comma y2, um, they have common point. Oh, sorry, they don't have any common point. They are disjoint. Each of these each of these six subsets are path connected. So that means what I want to point here is that here x cross y has here x cross y has six path connected component. How this will help, that I'm going to prove, but how this particular fact, whatever I proved, that xy2 topological space, if x has two path connected component and y has three path connected component, then x cross y, the product topology, will have six path connected components. So on the base of this I will prove theorem 12 directly. Okay, this question 12 directly. What question 12 says, B denote the set of invertible triangle n cross n matrix with real entries. Then B has one path connected component, two path connected component, 2 to the power n path connected component, 1 plus 2 to the power n path connected component. What, let B be the set of all invertible upper triangular matrices, right? Invertible upper triangular matrices. So arbitrary element, this is, I'll write B. So take 2 B, I will take x and y. B, x is equals to something like a11 a1n 0 a22 a2n, like this way, 0 0 0 ann, like this way. That is the main diagonal, and this will be like 0. This is the upper triangular matrix X. Now for any x belongs to B, as x is invertible, all ai is not equals to 0 for all I equals to 1 to n. That means main diagonal element will be non-zero because a is elements of B are invertible. That means main diagonal element will be non-zero. If there is 0, then they will not be invertible because determinant will be 0 in that situation, right? I hope it is clear. So that means all element will be invertible. Now consider a function gamma from 0 1 to the space B. How it is defined? Gamma of t is equals to a11 a12 t going to a1n t. Next is 0 a22. Next will be a23 t a2n t. In that way, this way 0 0 0 0 and ann. That means except the main diagonal, I have multiplied t to all the element. Okay. Then you know the standard way to take a path connecting x and y 2 point coming from the topology x is gamma from 0 1 to x, gamma of t is equals to tx. This is standard. You are asking now that how to take a path. This you can remember that tx plus 1 minus ty, but make sure tx 1 minus ty and tx plus 1 minus ty all make sense, and this sum is again in x. Okay, then you can take this is as a path always. If we have a topological space x for which for any real number t, t of x and 1 minus t of y, they are making sense, we can add them, and the elements is again in the topology x, then we can directly give the path connecting 0 and connecting x and y 2 points. Then you can look at 0, gamma of 0 is equals to main diagonal function. That means a n n. This is 0, all main diagonal except main diagonal, all will be 0. And gamma of 1 is equals to x. That means, and also note that gamma of t is upper triangular matrix x, right? And the way I have defined gamma t, that determinant of gamma t is non-zero, because determinant of x is non-zero and determinant of x is product of a1 a2 an. Okay, so gamma t is in b, so that means gamma t is a continuous path connecting identity, sorry, no, not identity, connecting a diagonal matrix A11 ANN 00 to X, to the main matrix X, which is equals to basically A11 A1N 0 A22 A2N, that way ANN. So now what I could, that we can always give a path from identity to a matrix. So that means from here, that means what we can say, that number of path connected component, number of, and let D be the space of all invertible diagonal matrices. Okay, I'll take 5 more minutes, please. Okay, D be the space of all invertible diagonal matrices. But this is very interesting problem. Okay, D be the space of all invertible diagonal matrices. What I want to say here is that what we have seen, that for every path connected, sorry, every upper triangular matrices which are invertible, I will able to get a path connecting that upper triangular matrices, invertible upper triangular matrices, to a invertible diagonal matrix. That was my point. Okay, but also, so that means, and that is the thing will assure that so it is enough, so number of path connected component in the diagonal matrix is same as number of path connected component in what is called X, sorry, B, the space B, invertible upper triangular matrices. The number of path connected component in the invertible upper triangular matrices is same as the number of path connected components in the space D here. Okay, D means diagonal, only invertible diagonal matrices. And now number of invertible. Now you can write what is that. This D is particularly, this D can be written. This particular D can be written. You can say D can be written as, we need D is an invertible diagonal matrices. I can take D as A11, or I can take X11 Xn such that Xi not is equals to 0. That means this is in R to the power R minus 0 whole to the power n, right? I mean, every element of D is a diagonal element. Okay, this is something, every element of D is something like x1, x2, xn, and as this D is the collection of all invertible diagonal matrices, that means each of xi will be non-zero. That means this D is particularly subset of R to R minus 0 to the power n. But R minus 0 has two path connected components, has two path connected component. That implies R minus 0, this is not only, this is exactly isomorphic. R minus 0 whole to the power n has 2 to the power n number of path connected component. This is coming from the fact path connected component. Okay, this is coming from the fact that if x and y are two topological space, x has two path connected component, y has three path connected component, then x cross y with product topology will have six path connected components. So this is the same way we can say. This is the same way we can say. So B have 2 to the power n path connected component. That gives the B have 2 to the power n path connected components. Is it clear? Is it clear how this theorem is proved? If you, this is not, you can, I think you should read this one because this is very interesting. Why this is interesting? Because first, what is that? If x and y are two topological space and x has two path connected component and y has two path connected component, then x cross y has a path connected six path connected components. Now what we have given is there here is that B is the set of all upper triangular invertible upper triangular matrices. As B is invertible upper triangular matrices, main diagonal element will be non-zero and the upper, and now we can give a continuous path from 0 1 to B connecting a invertible diagonal matrix and a upper triangular matrices. That means if we can think that the space of invertible diagonal matrix and the space of invertible upper triangular matrices, then number of connected component path connected component in invertible diagonal matrices is same as number of path connected component in invertible upper triangular matrices. But as the number of path connected component in the space of all invertible diagonal matrices is same as 2 to the power n path connected component, so that will give that B has 2 to the power n path connected component. Is it clear? Okay, so if you have any time, then I will discuss one more problem, otherwise I will stop. Be interested? I think I can discuss at least one more problem. From I have discussed 12, I can discuss directly then 13. 13 is also same way, so I can discuss very fast. Okay, I'll discuss 13 very fast. I'll just take.
Sir, can we discuss 14 instead?
Okay, 14. Okay, thank you. No problem. I think 13, the way 13 is proved, the same way 13 and sorry, the way 12 is proved, the same way 13 and 15 can be proved. Okay, 15 answer will be 2 to the power L. You can directly look at that GL. Okay, I'll just if you have the access of questions number 15, this is the 14, right? Okay, 14 I'll discuss. 14 I'll discuss and I'll then stop. Okay, I'll 14 discuss, but okay, I think this is 14. I don't know why this is small. Okay, this is 14, but fact is that 15. I'm just trying to 15. How 15 will be proved? I will write rapidly 13 and 15 and not discuss. Just 13 and 15 I'll say and then go to 14. It is clear that from 15, if you have the question, then you can look at that number of path connected component will be equal to the number of path connected component of GLNR, number of path connected component to the power L. This is the thing. But GLNR, if you look at GLNR plus, this is path connected. That proved, sir. Similarly, we can show GLNR minus, this is path connected. That means GLNR has two path connected component. So number of path connected component of GLNR is 2. So from the similar technique, whatever I have used in 12, that similar technique will give the number of path connected component in the space P in 15 is 2 to the power L. Okay, and similarly for 13, I think that will be 2 to the power n minus 1 because that will be like T denotes the set of upper triangular matrices with real entries and with determinant 1. Yeah, there will be the similar that. Then 13 will be what? 13 will be that the number of path connected component is same as the number of path connected of D dash, where D dash is the set of all diagonal matrices with determinant 1. That means all those I can write it something like x1 x2 xn such that this product x1 x2 1 is 1. So that that is equivalent to r to the power n minus 1. Okay, that is equivalent to r to the power n minus 1, because this x1 x2 xn is equivalent to r to the power n, but one extra equation will drop one more dimension. Okay, so D dash is the set of all diagonal matrices with okay, for I'll just write this one, just like not only write all thing, but okay, this is 13. The cardinality or number of path, okay, this is so 13. I'll just write 13, one line that will give 13 solution. Number of path connected components of T, that is same as number of connected component of D dash, where D dash is equals to the diagonal space of diagonal matrices, set of all diagonal matrices with determinant 1. That means I can write it x1, x2, xn coming from r to the power n, such that this product x1, x2, xn is equals to 1. This is unitarily equivalent to r to the power n minus 1. Not r to the power n minus 1, r to the power n minus, r to the power minus 0. And this will be like, this is the point not coming from r to the power n. This is the point coming from r to the r minus 0 whole to the power n. Okay, so this will be the r minus 0 whole to the power n minus 1. But r minus 0 whole to the power n minus 1 will have 2 to the power n minus 1 component. So this will prove. Okay, now I'll directly write 14. And 14 I will also write, I don't, okay, what is the question? Which of the following subsets of NR are path connected? Set of all symmetric matrices, all of whose eigenvalues are non-negative. Oh, just 1 minute. Okay, I have written, I don't have. What is the 14? No, 14 is there. Okay, key was a set of all symmetric matrices, all of symmetric matrices, all of whose eigenvalues are non-negative. Okay, okay. So here, okay, consider for any A and B symmetric matrix in MNR. I'll write hint here. Okay, sorry, I will not be able to prove here. I'll write hint and prove in next. I think that will be enough even. Then consider F from 01 to 01 to MNR, how f of t is equals to ta plus 1 minus tb. Clearly, f of t is symmetric matrix. Okay, okay, and if f of t is symmetric matrix, if eigen value of a and b are non-negative, then symmetric matrix f of t, this is symmetric matrix, will have non-negative eigenvalue, will have non-negative eigenvalue. Okay, will also have non-negative eigenvalue. So that means what we have said, that we are able to give a function continuous. This function is continuous. This is continuous. That f is map 2 point connecting 2 point A and B, and that function. Okay, what is the important? I mean, what is the fact I am proving here is that if I take S is the space of first space, what is the space? Set of all symmetric matrices with symmetric matrices, all of whose eigenvalues are non-negative, all of whose eigenvalues are non-negative, this space, then I can give a map from 0, 1 to S for any A and B belongs to this particular set S, f of t is equals to ta plus 1 minus tb. Then what I have to prove, what I have to want to make that for every t belongs to closed interval 0, 1, f of t will be a matrix. That matrix will be first symmetric. That matrix, all the eigenvalues of that matrix will be positive, non-negative. Eigenvalues of that matrix will be non-negative. These are the these are the thing I want to show. So that means I can give a function which continuous and that connects 2 points A and B. So that means S is path connected. Is it clear? Is it clear?
Yes, sir, clear.
Okay. I mean that what is the thing that path connected means? That suppose I have a space. This is it. 2 point is there. I can't get the path from outside. I have to give the path from inside. This path is wrong. This is wrong. This type of path. If I have this path coming from outside, that path will not help. But the path inside the space is will help. So that's why I have to show that ft for every t, ft is in the space of S. This is in containing S. That is what I need to show. Similarly, set of all matrices with trace 1, that you can even show. Similarly, trace 1 will also be done. And set of all matrices for which x to the x transpose ax is greater than 0, that is also can be done, not a problem. But set of invertible will be little problem. So that I think I will do. No, set of invertible also done. I think after this, whatever hint I have tried to give, after this try to read the solution. Otherwise, will be done in next class.
Okay, sir, I will try tomorrow,
Yeah.
and
Sorry,
then
sorry. I
let's.
actually, yeah, actually, this is too beyond. I think I'll try to discuss 14 and 15 in the next class fully. Okay, don't worry. Okay, so I'll stop here. Okay,
Okay, sir. Good night.
good night.